Hello, folks. All right, it's time to put the next piece of the puzzle in. So, a little bit of new content today. The notes are very, very short, and I am going to take us back. I want to make sure that I have that on the screen here, real quick, so I'm ready to switch over. All right, so we have talked about wavelengths, frequencies, wave reflections, fundamental harmonic frequencies, and overtones. Several other terms. Can't even remember all of them. Seems like a lot of terms have gone in the last couple of videos. So, next step of the puzzle is we need to measure the speed of the wave. Okay, so we got a couple of equations going in. Finally, we got some math to deal with. So, obviously, if I drop a rock into a puddle of water, the wave will propagate outwards two-dimensionally from there. And I could obviously time how far the wave travels in a specific unit of time to calculate the wave speed. So v equals distance divided by time, just like normal. Okay. Problem is, for a standing wave, even though the standing wave is moving as the wave begins to propagate back and forth, because remember, a standing wave forms when there's waves formed by going one way and reflected off and coming back the other direction. It's going to be kind of hard to measure the wave speed on that because of the standing wave pattern. So we need a different way to measure that. So instead of thinking about distance and time, it's easier to think about distance just being the length of one wave. Since the standing wave pattern is formed, we can easily find this wavelength. But then to time this, usually we don't have a stopwatch to deal with, so as long as we know the frequency, which once again, if this is one wave, then the time interval is the period of the oscillation, and the inverse of period is frequency. So instead of distance divided by time, we can calculate the wave speed by going wavelength times frequency. And once again, make no mistake, this is still distance divided by time. It's just rearranged a little bit. So your distance is one wave, and instead of divided by time, we inverse that and multiply it by frequency instead. So wave speed is still meters per second because we have a length in meters and a frequency in hertz, but remember, frequency is just 1 over seconds. Okay, so there's your first equation. Now, when we're specifically talking about the speed of wave on a string, what's funny is we can calculate it by knowing the wavelength and frequency, but the the speed of a wave on a string does not depend on the frequency and wavelength. What it actually depends on is the tension. So when we have a wave that forms on a string, the tension and another variable called the linear mass density. Okay, I'm going to give you a little warning here as we get down to this equation. Linear mass density is simply the mass per unit of length. So it's mass divided by length. This is sometimes symbolized with the Greek letter mu, just like our coefficient of friction symbol. So you may see that in equations as well. So if I have a string that is set to a wave generator on one end and I'm holding the other, as I begin to pull it more taut, then what's going to happen is it's going to change the tension. So standing wave patterns will only form when I can match that tension up to generate a wavelength that follows one of the fundamental modes of vibration. All right, so it's a lot to take in. I realize that. I'll show you here in a second. So this means that speed is a property of the string itself and not dependent on the wavelength and frequency as long as the string length does not change. So this needs to be a rigid type of string, not a string that's kind of you can't use a rubber band on this because that changes the linear density. So that throws this equation all off if we use a flexible type of string. All right, so our equation to find the speed of a wave on a string is the square root of the tension divided by the linear density. Okay, and we can generate the tension several different ways, and one way to do that easily is by just hanging a mass of known value off the end of the string to generate a constant tension. Okay, so let's go ahead and switch over and show what this means. All right, so here's the equation I was talking about. Notice that this is force tension divided by this mu, and this mu is mass over length, okay, of the string. All right, so we have a 4-meter long string. It gives you the linear density down here. And we have a 45 hertz oscillator, and we have one of the modes of vibration here. And we've got the mass times gravity is Ra 16.3 newtons. As I change this tension up a little bit, notice that a standing wave pattern no longer forms. Okay, but I can reach another mode of vibration by changing the tension of the string. So as I increase the mass over here and I increase the tension, now we get another mode of vibration that's a standing wave pattern. So once again, if we go through this and I pause it, we have one wave here and we have 2 waves here. So if the length of this string is 4 meters, that means that one wavelength is 2 meters. Okay, so we should be able to find the speed of this wave by knowing the wavelength and frequency, but I can also find the speed by knowing the tension and the linear density of the string. Okay, so that takes us through that. Mr. McDonald's going to do a couple of practice problems on some of this stuff with you guys, and hopefully that's the last video for a couple of days. Can't promise anything though. Okay.